Hello YouTube and welcome to What the Math. In today's video we're going to be using Universe Sandbox 2 and exploring new features of version 13.1 of Universe Sandbox. Specifically we're going to be actually using something called, here they actually added the feature right here, something called Tidal Heating and Tidal Evolution. These are the new two features that have been added and they're actually pretty awesome. And we're going to also use these features to explore some of the inconsistencies from the movie Interstellar. If you watch the movie, you'll see what I mean in a second. But before that, let's actually create a completely new solar system. Actually, it's going to be not a solar system, but a jovial system. Jovial system refers to a system of Jupiter. I'm going to place a Jupiter right here. And this is going to be our center. So if we look at it, it's rotating, this is the mass and the temperature. Minus 273 Celsius because there's actually no sun around it, so there's nothing to heat it up. Now, what is tidal heating? Let me actually introduce this to you by showing you an example. I'm going to decrease the time first. I'm going to enable tidal heating right here. I'm not going to touch this yet. I'll explain this to you in a second. And now we're actually going to take Venus, not Earth, because Earth seems to be a little bit bugged right now. It doesn't actually change its temperature, but Venus does. So I'm going to place one Venus right here, right next to it. One Venus a little bit further away, one a little bit further away, and then maybe one more here. And then actually let's put one more over here. So there's, what, 5 Venuses, Veni. Now what I'm going to do is, well, let's actually start with this one, the one closest to Jupiter. And just look at the temperature. Look at how it's skyrocketing. I'm going to decrease the time just so it's a little bit more accurate. This is almost 1 second per second. And look at how fast the temperature is increasing. It's 144 degrees, 145, 146. It's 1 degree per second. Why is this happening? And as I explain this to you, let's just look at what happened to Venus. What is going to happen to Venus? Why is this happening? Well, this is happening because of something called tidal heating. Basically, because the Venus is so close to such a massive body of Jupiter, and because Jupiter has such a strong gravitational field, it's essentially exerting its gravitational forces onto, oh, look at that, look how beautiful this is, the Venus is on fire. It's exerting its forces on 2 different spots of Venus. One is right here and one is right here. And because of these differences, basically what happens is Venus is stretched and pulled in such a way that it's kind of like rubbing your hands really fast, but across the entire volume of Venus. So basically there's a lot of rubbing and scratching going on because Venus is actually spinning. Ooh, bugged out there for a second. Venus is spinning, but it's spinning differently from how it rotates around Jupiter. And because it spins so differently, it is basically being heated up by the gravitational forces. So there's a gravitational force here that's different from gravitational force here, and it creates this huge frictional element that heats up Venus. It's actually going to be several thousand degrees warm. But if you look at the one that's slightly further away, oh, and by the way, you can see the tidal power exerted right here. It's actually 5.33 to the power times 10 to the power of 15 megawatts. So it's actually pretty high. I don't know if this is accurate. It doesn't sound like it might be precisely accurate, but sounds pretty cool nevertheless. This Venus right here gets a little bit less, actually 100 times less tidal forces, so it doesn't heat up as fast, but nevertheless it's going to get pretty warm here. So this Venus that's quite farther away gets the same kind of effect, but not as dramatic as this Venus right next to Jupiter. And obviously this one here gets even less, so this one here gets about 10 times less, maybe 50 times less, and this one here gets even less. And so as you would expect, the temperature of Venus farther away won't get as hot, and the Venus that's really far, Venus number 5, won't really get almost any tidal effects, or, I mean, there will be some tidal effects, but they won't be dramatic, and they won't really heat up the planet as much, so its temperature will probably stay the same. So let's actually observe what happens here, and then we're going to discuss this more in relation to the movie as well. But basically, there's a satellite of Jupiter called Io, and it's somewhere in relation to Jupiter. It's somewhere over here, somewhat close to where Venus number 4 is, and it does get a ridiculous amount of tidal forces. And because of those tidal forces, if you ever look at the picture of Io, it's covered in volcanoes, because basically its internal temperature is so high that it's really just one huge molten planet on the inside. And there's a lot of volcanism going on, a lot of explosions, a lot of fire. And it's basically like a fire planet because of, really not because of the sun, but because of the tidal forces that Jupiter exerts on it. So I'm going to accelerate time just a little bit so that we can actually evolve our planets a little bit further and then see, oh, look at that. Let's see how hot they get. So this Venus is going to get ridiculously hot really fast. Look at, it's already at tens of thousands of degrees. Now, I'm not sure if this would actually happen in real life because even though Jupiter is so close to it, I don't think it would actually get that hot. But it's possible, you never know. But basically, yeah, so this huge friction on the inside causes it to be really, really, really hot. Now, there's another feature that has been added, and that's tidal evolution. And what this is basically because of the gravity on different parts of the planet, with time, it will actually cause the planet to start spinning as fast as it rotates around Jupiter. What this means is, here, I'm going to enable this and hopefully this will work. I'm going to enable it and put another Venus right here and then another Venus right here. Let's see if this works. I'm not sure if it will, but it should. And basically, if you look at the rotation of this planet, it now rotates as fast as it spins around Jupiter. So it basically, just like our moon, it will always face the same way. Oh, okay, maybe not this time. This didn't work. It didn't actually evolve enough. It should evolve with time, but I don't think it will happen fast enough. It does take a little bit longer than that. But yeah, so here, what will happen eventually, it will actually acquire what is called a tidal lock. So it will be just our like moon. It will be tidally locked to Jupiter and essentially not receive as much tidal heat. Let's see if we can do it manually. Let's tidally lock it and see if this works. Oh no, it still doesn't work. Alright, so I guess it's relatively close to Jupiter, so probably that's why. So even though it spins with the rotation of the planet, I think in this game it's not really simulated really well. But yeah, it should be getting a lot less heat because of the tidal lock. Let's try this here manually. Alright, the tidal lock seems to not work really well, and the planets are basically getting overheated and super ridiculously hot. So this one is already at 8,000 degrees, and that's the one I just recently added. The first one that I added is at, is it 23? Or is it that one here? Yeah, it's 23,000 degrees Celsius, so it's ridiculously hot. Even the one that's second from, in the second orbit is at 5,000 degrees. But the ones further away are not that hot. This one just increases temperature by about 100 degrees. This one, this one is pretty hot too, 140 and increasing further. But these further ones are not. This one is minus 267 and this one is probably still minus 273. Yep, it is. So basically that's how tidal heating works. Now, I'm not sure if I explained this really well, but basically, let me try this again. And now let's do all of this using a black hole and simulate the black hole from Interstellar. So I'm going to place a black hole right here in the middle. Oh, I should probably start a new simulation. Also enable I need to enable tidal heating. I'm not going to be touching tidal evolution because I'm not sure if it actually works yet. I do seem to have a bit of a problem using it, but tidal heating does work. So let's place a big black hole, actually bigger than this, change its size to 100 million times the mass of Sun, rename it to Gargantua, and it's somewhere here. There it is. We're not going to replace a neutron star because basically it will give us extra heat that we don't actually want, and we want to just use tidal heating, nothing else. So let's just decrease time acceleration and place our first planet. And the first planet is going to be basically similar to the planet we see in a movie that is Miller's planet. And if you're paying attention, this actually looks exactly like Venus because it is Venus. I renamed it. But basically this is it. It's at 6 astronomical units, or basically 6 times the distance of Earth from the Sun. And Gargantua is right there. So I'm going to accelerate time and let's see what happens. As you can see, tidal power right now is 1.13 times 10 to the power times 10 to the power of 14 megawatt, which is actually just as high as that second Venus was from Jupiter. I'm going to accelerate time and let's see what happens to it. And as you can probably guess, well, not yet, but in a few seconds it will start warming up. There's a few glitches still in this alpha version where tidal heating doesn't actually kick in right away, but it will start warming up in a second. If I add a new planet, same distance, you'll see this right away. And there we go, I actually accidentally paused my game. And look at how fast the temperature is increasing. It is ridiculous. It's actually increasing faster than I actually thought it would. Now, what is happening here? Well, just once again, this is tidal heating. Because the planet is spinning differently from its rotation around the black hole, it's experiencing huge tidal forces on two different points across from on its surface. And because of that, they're being pulled and stretched in such a way that it's kind of like really just rubbing your, well, not good, that's probably not even a good example. It's just kind of like taking something and stretching it over and over and over again, stretching and pulling until the inside parts of the planet start releasing huge amounts of friction and really just warming up and heating up the planet inside, from inside out to ridiculous temperatures. This is kind of like what a microwave oven or the way microwave oven actually heats up our food as well. It essentially starts oscillating the food water molecules inside our food, and really the heat from the inside of the food that is inside microwave oven gets heated up to such an extent that it's just really fast and it's really efficient. But now this is not microwaves, of course. This is a gravitational pull, so it's slightly different concept, but the idea of being heated up from the inside is quite similar. So if this were Miller's planet, that's 6 astronomical units from the surface of Gargantua, from the event's horizon of Gargantua, this is what would happen to it after, what, 1 hour, 1.7 hours. It would get ridiculously hot. Now, according to Kip Thorne, the physicist who was responsible for doing all the calculations, according to him at least, Miller's planet did not really rotate. It sort of, it did have a tidal fix. It did have a tidal position lock, or sorry, tidal lock. And that means that it was kind of spinning and rotating, facing Gargantua, always, basically always exerting the same face toward Gargantua, but it had a slight wobble, just kind of like our moon. So in other words, what it did is, it didn't just face Gargantua like this, it also wobbled a little bit, back and forth, and this is why, according to him, we see the waves, the tidal waves in the movie. Now, even if it wobbled a little bit, just like this, like he said it did in the movie, where is it? Let me just show it to you again. The tidal power would still be quite great. It would be so great, in fact, that the planet would still be relatively hot. Now, this is still warming up, and you'll see how hot it gets in a few seconds. But just for fun, let's place a few more Venuses, or Veni, I'm not even sure what plural is, around Gargantua and see how things change if we're farther away from it. So let's place one here, let's place one more here, let's place one more here, and just for fun, let's place one really far away. And let's see what changes in terms of temperature. So this Venus right here is at a distance of 10 astronomical units, which was pretty similar to, I think, one of the other planets, possibly Man's planet. I forget which one it was. No, sorry, not Man's planet. Man's planet had a very eccentric orbit. This would be that other third planet, which I believe was called Edward's planet. And even here, the temperature is going to increase. Now, Man's planet had a very eccentric orbit, so we're actually going to simulate this as well. But it did approach Gargantua at some point of its orbit for maybe a few minutes at least. So definitely a few minutes, but possibly even an hour. It would pass by Gargantua at a very steep kind of steeply inclined orbit close to Miller's planet. And we're going to try to simulate this by taking yet another Venus and changing its orbit slightly. So I'm going to pause this for a second just so I can change its orbit to Alright, that kind of works. So there's another planet, another Venus planet. I guess I should probably rename it to Man's World. That's the cold world that we see in the movie. And this one here has the highest point of about 190 astronomical units and the lowest point at about 5 astronomical units, so it's relatively close to Gargantua. And let's actually see if there is going to be any kind of a heating effect when it gets close to Gargantua. I'm kind of actually curious what's going to happen to it, but meanwhile let's take a look at some of the other planets that we've added. So this is our original Miller's planet, and it's already at 8,000 degrees Celsius. So that's basically all result of nothing but heating from the inside. It's basically being molten from the inside by the ridiculously high tidal forces. And this planet right here, I'm going to rename it Edmund's planet, because I think Edmund's planet was at approximately 10 astronomical units. This one is at 11. So let's actually see what happens to it as well. It is slowly warming up. And there is no neutron star anywhere to help it warm up. So I'm going to just accelerate time, and then we'll see what happens. Let's get this to max possible before my game starts slowing down and crashing. Can I go a little bit faster? Alright, so let's just wait and see what happens. Now, as you can see, Edmund's planet is also increasing in temperature to a ridiculous amount of almost 200 degrees Celsius. The only planet that's not really increasing in temperature is this other third Venus, as I guess call it. It's slowly increasing, but not enough to influence its actual temperature. But we'll see what happens after, let's just say, let's get this to a few days, maybe a month after we've created this system. And it's almost a month. I decided to actually stop this here because my man's world is closing to Gargantua. It's actually in its lowest approach. It's close to its periapsis. So I'm going to slow this down and let's explore each of the planets separately. Actually, let's wait a little bit just until it gets closer to the black hole, maybe a little bit closer, and then explore this. So right about here. Perfect. Okay, so starting with the outmost. And the outmost planet, also known as Venus, is still at minus 273 degrees Celsius. Its tidal forces are relatively low, only about 500,000 megawatt, which is not that high when you think about it. In a second, I'll actually show you what the tidal power of Earth on Moon is, but anyway, let's keep going. This is Edmund's planet, and this planet is at 2,300 degrees Celsius. And that's actually at a distance of 10 astronomical units from Gargantua. So that's actually relatively high. Let's look at some of the other... let's look at Miller's planet. Miller's planet is at 9,500 degrees Celsius, and it's still increasing. It hasn't actually stopped increasing. But the planets that are not that hot... Well, this one is, the fourth Venus, is 270 degrees Celsius, but it's not molten hot as the other planets. And this one here is relatively cold. So the fifth Venus, I guess, is at minus 260 degrees Celsius, and its tidal forces are much lower. And this is at a distance of, let's actually check the distance here, at a distance of 23 astronomical units. So it's relatively far, and because of this, it doesn't experience as many tidal forces as the other planets. Now, big one is the man's world, the cold, super cold world that has an eccentric orbit, and ta-da, of course it is ultra hot as well. And not even just because it passes by Gargantua, or so close to Gargantua, but because of its eccentric orbit. It still experiences quite a lot of tidal forces, really everywhere. And on average, I believe this number is right here, 4.63 times 10 to the power of 11 megawatt. So this is basically how the Gargantua, the black hole in Interstellar, would probably influence these bodies of these planetary bodies as they would pass by or orbit around it. Especially man's world, because of its eccentric orbit. Every time it would pass by Gargantua, it would get heated up ridiculously high. So it would actually be ultra hot. And just to give you kind of a perspective on all of these numbers, so let's take a look at our solar system. Here's Earth and the Moon orbiting around it, and basically both the planet and its satellite exert tidal forces on each other. So we get those tides that we see from in the water, and Moon gets the same thing, but because there's no water, usually it gets it gets earthquakes or moonquakes in that case, and all kinds of other stuff because of the tidal forces from our planet. Now, obviously, Earth is bigger than the moon, so the tides that moon experiences are actually higher. Now, if you look at under temperature, this tidal power is only 12.7 megawatt, and that is about 50,000 times lower than what that Venus was experiencing at a distance of what, 23, I think it was 23 astronomical units, which would be equivalent of, is that how, yeah, that's a little bit farther, equivalent of a distance of Neptune, approximately a distance of Neptune from the Sun. So if there was a planet right here and this was a black hole right in the middle, it would basically exert 50,000 times higher tidal force on that planet than what Moon experiences from Earth. That's just to give you a comparison. But basically, yeah, this is how or why I think the tidal forces would probably cause all of the planets that were orbiting around Gargantua to essentially melt. The friction would be so high that they would melt from inside out. And I think I'm going to pause this video here. Hopefully this helped you understand the tidal forces and why they're important, and also gave you an idea of these new features in version 13.1. Unfortunately, if I actually enabled these features right now and I try to unpause my game will slow down dramatically because suddenly there's all these new calculations. So I think these new features possibly added a few bugs as well. But other than that, I am actually enjoying these awesome new features. Basically, the ability to heat up a planet using nothing but gravitation. Anyway, thank you for watching. Please subscribe and game you later, alligators. Bye-bye.